So today our presenter is Tom Elsden from the University of St Andrews. So Tom completed his PhD in 2016 in the solar and magnetospheric theory group at St Andrews. He stayed there for a postdoc with Andy Wright until September 2019 before moving to the planetary science group at Leicester to take up a Leverhulme Early Careers Fellowship, working primarily with Tim Yeoman. Then in September 2021, Tom moved the final year of his fellowship to the University of Glasgow, where he also held the position of Rankin Snedden postdoctoral fellow. In 2022, Tom moved back to St Andrews for his current position, which is a lecturer in solar and magnetospheric theory. So the title of Tom's seminar is Ultra Low Frequency Waves in the Earth's Magnetosphere. So I'll hand over to Tom now for your seminar today.
Okay, Rosie, thank you so much for the introduction. If at any point anyone can't hear me or see my pointer or something, Rosie, I'll trust that you'll let me know. Otherwise, I'll just be speaking in my office into oblivion. So that would be great if you could let me know. So hello, everyone. Thanks very much for having me here today. My research over the past 11, 12 years or so has focused on ULF waves. So the point of today is to try and give a broad background into mostly the theoretical and modeling aspects of that, because that's my expertise. I will be showing observations as well to set things in context. But the idea is that if you're not really a ULF wave person, hopefully you can at least pick up and kind of follow along some of the key points from today. So that's the general idea. I'm hopefully not going to go too deep into any one thing, but just sort of cherry pick a few of the key points. Let me see if I can advance slides. Yes, I can. So outline. So I want to start with some of the first observations of ULF waves, and then theory, and then also talk a little bit about nomenclature. ULF waves is one of those fields which suffers like probably every other field. If you're not in it, you don't realize all these different words that get used to mean very specific things that were created 30, 40 years ago, and everyone just now carries on using potentially confusing nomenclature for things. So I'll try to clear up some of that. Hopefully the first section on background will lead itself nicely into why ULF waves matter in the magnetosphere, why we care about them. So hopefully I'm going to spend the first 20 to 25 minutes here, and then maybe the last sort of 10 to 15 minutes or so here. Again, Rosie, for time, just please let me know when you'd like me to stop. So I'll go through some research highlights and then future directions, sort of some large scale ideas at the end. So this is the slide that I use for, essentially I've been using this slide to introduce ULF waves for a long time. The bottom right-hand picture is something that will be appearing in later slides as well, as a cartoon, a schematic to describe the key wave processes going on. I think it does its job quite nicely. So what are ultra-low frequency waves? Why are we here? What are we talking about? So fundamentally, we're talking about oscillations of Earth's magnetic field in a particular frequency band. So they're in the rough band of 1 millihertz to 1 hertz. So very much on the kind of the lower end of the frequency spectrum. And in particular today, we're going to be looking at this lower end. So much more on the millihertz side rather than the hertz side. The reason this is important is once you get higher than this, you start to get into the frequencies of various particle gyro radii, and that's very much not the realm that we're going to be in. These things were first observed by Stewart in 1861. This was written up following the Carrington event. And there was, in the ground magnetic field data they had at the time, they were seeing some sinusoidal oscillations. I've got an example of a much later study by Nagata in 63, looking at that, just to give you an idea as to what these things look like. So we'd have time along the bottom, a couple of hours worth of data up here. And we've got the three components of the ground magnetic field for conjugate magnetic field stations. So these are on the same magnetic field line. And you can see these nice sinusoidal like oscillations in the different components of the field. And so that's kind of what we're looking at when we're thinking about ULF waves, these nice kind of periodic oscillations of Earth's magnetic field. What do they do? And probably the broadest description I could give of why they might be important is that they transfer energy throughout the magnetosphere, and they also couple different regions together. So coupling of different types of ULF waves can take energy from one place and deposit in another. So it's kind of important for the overall energy propagation through the magnetosphere. And the way I like to think of them is overall as responses of Earth's magnetic field to changes in its equilibrium. So we'll move to this little schematic in the corner here. we have the solar wind on the left and the Earth here, and the black lines being the Earth's magnetic field lines. And you can imagine that if the solar wind was just a nice steady flow, this system wouldn't be, it would be in some equilibrium, okay? It wouldn't be being perturbed at all. But because the solar wind is not steady, it's like kind of banging on the surface of a drum. So this, the magnetopause here, the pressure balance boundary, is constantly being perturbed, and that's launching these waves into the magnetosphere. And I'll come back to the schematic to describe the different types of waves that we see later on. But we're very much thinking of large spatial and temporal scales. So you can see here some pictorial evidence of these waves. And we're very much thinking of things on the size and scale of the magnetosphere itself. And that's how they end up in these kind of long temporal scale, low frequency regime. So that's what we mean by ULF waves. Generally, how these things are generated, I know I sort of mentioned the constant buffeting by the solar wind as being one, and I'll come to that in a minute. But generally, we split the generation mechanisms for these waves into two distinct groups. So that's forces external to the magnetosphere impinging upon the magnetosphere, and then waves which are generated through internal means. So externally, we have this kind of what I mentioned before. So dynamic pressure fluctuations in the solar wind, or changes in the density as well. You can kind of have periodic density structures which impact the magnetosphere as well. And these were found to be kind of correlated with the most highly correlated measure with ULF wave activity. So that's like driving on the magnetopause here and launching waves into the interior. You can also have Kelvin-Helmholtz and stable flanks. So you have surface waves on the magnetopause boundary and the flanks. And you can also have these things called dayside transients. So this basically lists a whole bunch of phenomena, things like magnetosheath jets and hot flow anomalies and force shock bubbles and all these different types of kinetic features, which can cause pressure disturbances on the magnetopause boundary and launch ULF waves into the interior. Then internally, we have wave-particle interactions. So this is where, through a variety of mechanisms, waves and particles can interact and exchange energy. And I'll come on to this towards the end of the talk. And you can also have flows or particles injected through substorms. So you have reconnection of the tail, which drives particles and flows into the magnetosphere from the night side, and these can generate wave activity as well. So these are kind of the broad distinctions between the different types of ways in which these waves are generated. I come from a group where we think very much of, well, we basically study MHD is broadly what the group in St Andrews does. Most people here study the sun, but myself and Andy Wright are the magnetospheric islands within that group. And because ULF waves have very large spatial and long temporal scales, that allows the use of the MHD approximation. If you're looking at smaller scales, then you need a kinetic description. And so broadly speaking, in the cold plasma or thinking of the cold plasma in the magnetosphere, there are two wave modes from an MHD perspective, which are important, and that's the MHD fast wave. And so this is kind of like the sort of lime greeny one shown here. Fast waves are compressible, they can propagate in all directions, and they're driven by magnetic pressure disturbances. So you can imagine that the buffeting by the solar wind is launching fast waves which can propagate throughout this whole domain. Okay, and then you have the MHD Alfvén wave. This is the best way to think of this is just like a wave on a string. So this wiggling field line here where it says resonant magnetic field line, you can think of that as an Alfvén wave. And these are transverse, so the displacement is perpendicular to the field line. And they're field aligned, so they're guided waves, so that their pointing flux or energy is along the field line. And they're driven by magnetic tension. And so broadly speaking, we can think of these two distinct wave modes. It's a kind of clean way to try to separate different waves in the data. And just a more theoretical point here, if you have a uniform medium, then these waves are decoupled, but as soon as you have any non-uniformity brought in, say, by a dipole magnetic field structure or changes in the density, you actually have a coupling between these different wave modes. And that's going to take us to our next part. So it was Dungy back in 1954 who first theorized that these kind of like the waves we saw in the first slide, hopefully it's skipping between those quickly enough for you. These kind of waves that you were seeing, okay, this was a later observation, but from previous observations, these long period kind of sinusoidal oscillations that we're being seen in the ground data, that these could be Alfvén waves that are standing along geomagnetic field lines. And this was later confirmed observationally. And this is kind of my favorite, one of my favorite review papers. So again, the point of this talk, hopefully, is to sort of give you a little bit of an overview of ULF waves, but also show you where you'd want to go for any more information. So this review written by Jeff Hughes is one with a kind of theoretical, historical perspective. So it shows you how the field developed over time. And so as a kind of newer student coming into this, it's a really nice place to start. Unfortunately, they spelt toroidal and poloidal wrong in their images, so it's toroidal and palladial, which should be toroidal and poloidal. But what it's showing here is the rough magnetic field structure for these different alphanic perturbations. So if you've got the magnetic field here, and you're looking at a toroidal oscillation, so toroidal meaning an azimuthal perturbation to the magnetic field. Again, confusingly or not confusingly, depending on how you think of it, we use the magnetic perturbation to define whether we mean poloidal or toroidal, not the electric field perturbation. So toroidal perturbation means an azimuthal magnetic field perturbation. That would be a radial electric field one. So it's a bit confusing that way. But what you can see is that there's if you pin the ends here, if it has nodes on the north and south, then you'd have a kind of fundamental oscillation here. And you could have higher harmonics of these as well. And you could also have radial oscillations of the field line shown here with the dashed line as a poloidal mode. So there's some kind of radial motion of the field line. And these different modes were confirmed observationally in a series of papers following this. But this was the first kind of idea that these things that we were seeing on the ground were alphane waves standing along geomagnetic field lines. So I've used this slide for quite a while as well, and every time I explain it, I kind of get a little bit, sometimes get a little bit deeper into it. And so I'm going to try and explain it as clearly as I can. If you've heard of field line resonance before, and it's a scary word that you don't want to think about, then hopefully today is going to clear that up for you. So this is also known as 1D alphane resonance from a more general MHD perspective. On the sun, you call this something different. But at Earth, we think of this as field line resonance. And so what we're going to use here is we're going to use these old lecture notes that I think Andy gave to me, and then I think these were from David Southwood. What you've got here is your dipole magnetic field lines of the day-side magnetosphere. And you could think of straightening these field lines out. So you've got the northern and southern ionospheres here. If you straighten those field lines out, you end up with what's called the box model, or the hydromagnetic box model, or the MHD box model. That's what you end up with here, with straight field lines, and then your ionospheres are on the top and the bottom. And what you're going to do is consider a density variation across here. Now, because you've straightened out the field lines, you've lost the inherent variation of the field line length that you would have had in the dipole. So this field line length and changes in the field strength would have given you a change in the alphane frequency. So what's the alphane frequency? The alphane frequency is essentially the period of an alphane wave standing along a particular field line, and that's going to depend upon the alphane speed, which depends upon the field strength and the density, and also the length of the field line. So because you've straightened this out, unless you put a change in the density, all of these field lines, just like if you imagine them as a set of uniform strings, they would have all had the same frequency. But by changing the density, we kind of mimic this change in the frequency that you would have had from the dipole. If you now do a little bit of theory and consider linearized low beta or coplasma MHD equations with a straight background field, and you go looking for certain solutions like this, where you're considering standing modes along the field line, so just sine or cosine profiles along the field line, and Fourier modes in time and in the third direction in y. We don't know what it's doing in z because we've got some variation in the density. So I should have mentioned, some variation in the density will change the alphane frequency through changing the alphane speed. And what do you end up with? You end up with perhaps a rather nasty looking equation, but it's just a second order ordinary differential equation, hopefully something we all met at university at some point or other. And it's got some nice nice points written in this particular form. So this was originally from Southwood 74, but I don't know if David's on the call, but I prefer the form written in Wright 94. You know, Andy had 20 years to perfect the dissemination of this theory, should I say. So it's in this form in Wright 94. And what you can see is in the denominator here, this omega, sorry, I should have said what this equation is for. This is for the Z component of the magnetic field. You could put this in any of the particular components, so it could be in the velocity or the other components of the magnetic field. Here it's in terms of the Z component in the magnetic field. All I really want you to take from this is the fact that you can make these assumptions about the geometry, you put this into MHD, and you end up with this kind of single equation that you can boil it down to. And then in the denominator here, this omega would be kind of like your fast wave frequency, and this omega A is your alphane frequency. And when there's a matching between these frequencies, you can have resonance. That's kind of the definition of resonance in some sense. And so when there's a matching between fast and alphane frequencies, there can be a resonance between these modes. And what do I mean by that? Maybe if I go back to my little schematic over here, what we're really talking about is that there's some frequency of fast wave, which can be, say, standing between two boundaries. This is kind of what the box model would say. There'd be some frequency of fast wave, and that can match the individual frequency of a particular field line. And where there's a matching between this fast wave propagating across magnetic field lines and the individual frequency of the alpha frequency of an individual field line, there can be a resonance between these modes, and there can be an energy transfer from the fast to the alpha wave. So I've showed you the maths for that, and you might go, okay, that's fine, Tom. I don't really take much from it. It's an equation I've never seen before using terminology I don't understand. Hopefully some numerical simulations will prove this to you in a nice way. And so this is kind of my favorite one for showing this. This is from Ian Mann back in the mid-90s. And what it's showing is 1D, very kind of simplified, a simpler simulation really as you could do to show this process. And what they've got here, what they're plotting in the left-hand side here is they're looking at the energy density, so the overall energy density of the waves. And you've got the kind of dependent, the 1D direction in X going here, and then the depth of the plot is time. And what they start off with is they start off with some initial conditions, some fast wave distributed throughout the domain, which you can kind of see by the peaks here. And what seems to happen is that all of this energy just builds up at a single location in time. And what's happening here is that there's a natural cavity wave. So there's a frequency of the fast wave trapped between the inner and outer boundary. And that has a particular frequency. And at the location where the alpha wave frequency matches that fast frequency, there's a coupling between the waves, and you end up with transfer of energy from one to the other. And you can see this on the right-hand side here. So this is looking at the azimuthal velocity. You could also look at the azimuthal magnetic field as well to see this. And at an early time in the simulation around this resonance location around x is 0.22 in this particular simulation, you can see that over time as you move from the solid line to the dashed line, that the amplitude of the perturbation is growing, and it's also narrowing its wavelength in time. This is through a process called phase mixing, where individual field lines which have different alpha frequencies drift out of phase in time, and that creates this shorter wavelength or sharper gradients between them. So this is kind of like about as simplified a numerical simulation you could do to show the transfer of energy from fast to alpha waves. Now this has some very kind of clear observational features, which is that there should be an amplitude increase and 180-degree phase change across the resonance. So you can see here that if you were to kind of look across this region, you see the amplitude or the amplitude of the wave peaks, and also that there's a phase change. It goes from positive to negative as you cross the resonance. And that should be visible in the data, and indeed that's exactly what you see. So here's a couple of observations from ground magnetometer data, where you can use latitudinally spaced chains of magnetometers. So these are, again, maybe I can go back to maybe this little schematic will do it for me. If you imagine these different field lines here, if you put a chain of magnetometers going along here, you're mapping out to different locations in space. And the resonance is going to exist on one particular field line. Okay, there'll be some width to that resonance. And so as you move latitudinally upwards, you should be sampling these field lines which span the resonance. Okay, and so as you move up in latitude, you're kind of moving sort of, you're sampling these different field lines, and you should see this amplitude change or amplitude increase in phase change as well. And so that's what these papers did. So in latitude, you could think of this like mapping to different L shells in the equatorial plane, if you will. And they've got different frequencies of waves that they were looking at here. And you can see that in each of the frequencies, there's an amplitude peak here. Same in the plot on the right-hand side as well. We have amplitude peaks across given latitudes, so particular field lines where they're resonant. And then you also see this phase change. So I think this is really nice that you've basically taken like a 1D MHD model and theory, and you've been able to come up with really the simplest tractable theory you could. And then that just pops up straight away in the ground data. I think this is like a really nice kind of coupling of theory and observations. It's sort of what you dream of as a theorist, that you come up as a modeler, you come up with some ideas, and then someone just goes and finds them in the data, and it's so clean and nice in that way. There's another example of that as well for field line resonance, and that's poleward moving auroral arcs. So here's a couple of examples. This one's by Rankin et al. 2005. There's also a nice one by Steve Milan in 2001. And what we're looking at here is all sky camera auroral images. So in the top right, if I move the little video box, And you can see these brightenings in auroral intensity appearing and then sort of disappearing off toward the poleward edge and being replaced by another one in this kind of wave-like periodic pattern. And this is consistent with the phase structure of within a field line resonance. I'm going to show you a movie later on, which I'll come back to confirm this. You can look at a keogram of this as well. So we've got time and then latitude here, and you take slices through this data and then stack them up in time. And you can see this poleward moving structure. And that's to do with the phase motion of a field line resonance. As I say, I'll come back to that later on. But it's just, again, really nice that you've got these images of field line resonance as a process just happening before your eyes, validating this kind of the simplified 1D theory, which explains quite a lot of it. So that's kind of really a nice part of ULF wave theory. One thing I guess I have to talk about is the cavity waveguide. I might call it a debacle, but the nomenclature I think is slightly confusing to people not in the field. So there was back in the early 90s, there was quite and you can see this, basically ULF waves had their heyday in the 80s and 90s, and then it's been on a slow decline ever since until they realized that they were affecting particles, and then it's kind of peaked again, and hence why I still have a job, which is great. But there were these so-called magic frequencies. So there were seemingly these frequencies that kept being seen in the data. And it's still not actually really resolved. I come down slightly on one side of it, but the idea was that the magnetosphere might have a sort of general size and shape that it has more generally than more often than others. And given that size and shape, that particular cavity, depending upon the distance, say, from the magnetopause to the plasmapause or so on, that would have a preferred set of fast frequencies, so cavity frequencies, which could then couple to field line resonances. And that's why on the ground you were seeing these preferred frequencies. And so these are called cavity modes, these global eigenmodes of the outer magnetosphere. And so Kivelson and Southwood kind of laid down the landmark papers in that respect. And then follow-up studies looked at relaxing some of these assumptions. So cavity means that you have a closed cavity. You could think of it either in a box model or in an axisymmetric kind of cylindrical model, where essentially it's closed and you've basically got a closed box in some sense, and your waves exist within that closed box. A waveguide mode allows for an open-ended boundary and flow into the tail. And so it gives a slightly different boundary condition and puts slightly different restrictions on the types of waves that you can get. And so that's this cavity waveguide nomenclature debate, I would say. And I think there's been evidence seen of both of these things, and both terms are still used regularly in the literature, which is somewhat confusing if you're just coming to it. So the idea is, sorry to kind of explain this schematically in a bit more detail. This is from Ray et al. 2007, and you've got you can have flow from the solar wind, and you can have modes which then propagate down tail as fast waves propagating across field lines, and then these couple to field line resonances at the particular field line which matches where the alphane frequency matches the fast frequency, and this would be the idea behind the waveguide mode point of view on this. So just to mention that I can't talk about ULF waves and not talk about cavity and waveguide modes. And then just one more thing on this is looking at so in terms of these magic frequencies, how does a cavity respond to a broadband stimulus? So if you looked at the solar wind, it's often not some periodic driving. It's very stochastic or random in the fluctuations. And so some work by Wright and Rickard in the 90s looked at this. So if you look at the top left, this is looking at the radial velocity. So what happens when you impose a driver like this on the magnetopause boundary? If you take the Fourier spectrum of that, you can see it's got a reasonably broad bandwidth over a certain frequency range. But then you look in the interior of the magnetosphere. So it's like saying the first plot there, is looking at what happens on the magnetopause boundary. You then look at what happens in the interior. And in a box model geometry here, they show that the cavity is a remarkable filter of this signal. So essentially the cavity's gone, I want to respond with a certain set of frequencies based on the size and shape and the magnetic field strength and so on. And you see that here, that if you take a Fourier transform of the spectrum inside, that you get these discrete frequency peaks. And that could be that's kind of the cavity mode idea, that you're driving in a broadband way, but the magnetosphere responds with this discrete set of frequencies, which are then the frequencies you see on the ground as these magic frequencies. That's the idea. I come down slightly on the side that it's more of a continuum, and you shouldn't expect to see these specific frequencies these specific points always at the same frequency. But that's maybe an argument for the questions if anyone wants to come back to that. And just to show some of this in data, because I'm very conscious of not just trying to, I mean, I'm doing this from the theory and modeling perspective, but I'm trying as much as possible to show you that these things have all been observed as well. So here's an example from Hartinger in 2012 of a global mode, or a global fast wave, a cavity or waveguide mode in spacecraft data. This is in Demis data. And what you can see are these nice, obviously that this data has been filtered in the red lines here. So this is the Z component in the magnetic field, the azimuthal component in the electric field, and then the pointing vector showing the direction of the waves essentially. And you can see these nice sinusoidal oscillations, and through the phase relations and so on, you could show that this is a compressional wave, consistent with an MHD fast wave. However, it's often difficult to find these kind of things in the data, and there's been a recent paper with Mike Hartinger of why this might be, why it's hard to find these kind of modes in the data, and they're often, for fast waves, not very large amplitude, and there's often other waves which cloud what you're seeing as well. So there's been a bit of difficulty in finding some of these things, but just to show you that there's spacecraft observations backing up this theory as well. So this brings me on to, I usually start the talks with this to try and keep people engaged so that they understand like why I'm talking about what I'm talking about. But I sort of thought I would present the theory first of kind of the background to ULF waves, and then explain why they matter so I can actually talk about the waves. So again, back to our familiar picture that you're now all rather bored of, but hopefully you're now familiar with it. So the couple of different regions together, how do they do that? Well, we've talked about this process of field line resonance. So you have this energy which can exist, it's a fast wave across field lines, and then it dumps it all into a single field line. That's as Alfvén waves carry field line currents, that's basically depositing that energy which was distributed across field lines onto a single field line. So you have this kind of energy transfer and coupling of different regions. Probably of most interest to people that I've not talked at all about so far, but we're coming to, is that ULF waves can excite particles to high energy through drift and bounce resonance. And so if you're interested in what's going on in the radiation belts and how you end up with such high energy particles, that's why people care a lot about ULF waves. And they can also recently have been shown to affect GIC, so geomagnetically induced currents on the ground. So this is kind of a space weather thing as well, to do with power grids and so on. And ULF waves have been shown to be quite or reasonably important in that regard as well. So this is why people care about ULF waves. I personally like them because I like waves, and I think a lot of mathematicians and physicists do just like them because they like waves, and waves are a nice tangible thing that we have lots of theory to describe. But it's great that they also happen to be of interest to practically. I'm being a little bit facetious there, so I should probably not do that, so that people still really believe that these things are very important, which of course they are. So I want to move now. So I realize I'm about, what's it, 11:30 just now. So Rosie, I was going to speak for maybe till about 11:45, if that's okay. Does that seem okay? 40, 45? You've raised a hand. I'm presuming that means that you're happy with that. So that's okay. Please do just stop me before that if that's not the case. So I was going to spend the next 10, so I spent sort of 20 minutes or so on doing 25 minutes on sort of introductory stuff with ULF waves, which is really, that's kind of the most important part of the talk in some ways, I see, is doing the background. And now I want to talk a little bit about some areas I've contributed to, and then also some areas I'm trying to get into. So I might, depending on time, talk about 2 or 3 areas. But first of all, 3D field line resonances. So what I spent the sort of tail end of my PhD doing with Andy Wright, and then following up in a postdoc, was looking at extending the ideas of classical ULF wave theory from kind of the 1D regime to what happens in a 3D non-uniform medium. And of course, the magnetosphere is 3D. The magnetic field and density structure varies in 3D, and therefore we need a 3D theory to deal with that. And so we wrote a few papers back then, and then really, if you're looking to get into kind of a summary of everything, we wrote a review paper with Alex Degeling for Frontiers in 2023, and that's probably where I would start to get an idea of what we're talking about. So it's all in there, and there's a lot more detail than I'll present today. And so it's important for dealing with inhomogeneities in the magnetosphere. And so what I'm showing an example of here is we put a plasmaspheric plume into our simulations. So I'm not talking too much about the background of the simulations today, but this is in the equatorial plane. The sun would be off to the right, magnetopause boundary where the simulation is driven, and then there's some inner boundary of the simulation. And it's this is a linear MHD model. And so there's some background density structure, And that's what's giving us the background density structure with a plume, so an enhanced region of density on the dusk flank, which is often seen in observations, gives us this kind of Alfvén speed profile. And what's shown on the right-hand side, I moved the little zoom box, is kind of the resulting Alfvén wave structure. It's the field line current density, which is a proxy for, as I said, Alfvén waves carry a field line current, and so we're looking at sort of proxy for the Alfvén waves there. And what hopefully you can see, even if you don't take anything else away from the plot, is that the waves look slightly different on this side than they do on this side. And essentially what's happening is the inhomogeneity in the density is causing inhomogeneity in the wave structure. And the one key thing here is that if you look at what's happening on the dawn side here, these waves are following, basically they're aligned with contours, so kind of constant L shell, they're following these circles. And these would have an azimuthal magnetic field perturbation or a radial electric field perturbation dominantly. Over here, however, they're kind of inclined inward, and this is kind of what we mean by the 3D element of it. And so this, the perturbations will be aligned or be tangential to these contours, and so there's going to be a little bit of a there'll be the amplitude will be split between radial and azimuthal components. That could become important for wave particle interactions as well. So really, this 3D nature, this inhomogeneity, has caused inhomogeneity in the wave fields, which is perhaps very obvious, but hadn't been shown before systematically. And so this is sort of what we showed with this 3D element of field line resonances, and this is still something we're actually kind of really still looking into as well. Now that the technology is back working again, this is a little movie on the right hand side here, sorry, left hand side here. And so what we did was, along with Jasmine Sandhu, her observations are on the right hand side, we thought we'll go looking for these in the data. So this is just a very similar thing to what was shown on previously. This is a movie, and you also see from the start here, you see these kind of inclined resonances forming, but you see this phase motion. This phase motion is what was giving you those poleward moving auroral arcs before as well. So you can see that as things move radially outward, they're moving from shorter field lines to longer field lines, and that gives you the poleward motion of these auroral arcs, but that's a separate story. And there's also some similar simulations by Alex Degeling, and he shows that you can see that the power in the electric field component is aligned with these contours of the Alfvén frequency. So you get these sort of strangely peaked distributions of the ULF wave power based on the Alfvén frequency. And so we went looking for this in the data, and so Jasmine did a really nice study where, so on the right-hand side here, we've got Timel on the bottom, and these are Van Allen probe observations. And you can see here in panel D, looking at the density, the electron density and the associated Alfvén speed, that what we've got here is a plume crossing, so the density jumps up and then jumps down again. And on this outer boundary of this plume, so this would be in kind of this location in this movie here, on the outer boundary of the plume, you see that there's these kind of strong radial and azimuthal magnetic field perturbations. And we were able to show, looking at the polarization and phase characteristics of this, that this was consistent with our theory of these kind of waves that you're seeing as you exit this plume. And so this was really nice, kind of, I was talking before about confirmation of theories and that being a nice thing. And so this was really nice to be able to have this observational confirmation of the stuff that we'd been looking at for the past 5 or 6 years. But we're going to be looking, I think, hopefully with Jasmine at some point of doing this more systematically as well, a lot more observations. So that was a really nice thing to be a part of. So thank you, Jasmine, for your great observations here. Right, this is the part where I get nervous because I'm talking about something I've never spoken about before. And also I'm talking about something I am not an expert on. So I'm kind of putting myself out there, and I'll hopefully spend 5 to 7 minutes or so talking about the potential for ULF wave particle interactions. And my broad idea is that I've spent all this time working on ULF waves. Most people care about ULF waves for the particles. I should probably also be caring about the particles. And so can I take my expertise in ULF wave theory and some of these new things that we've looked at in terms of 3D field line resonances and so on, can I take that and apply it into the effect on particles? That's my broad research plan for the next few years. So how do waves and particles interact? The primary interaction mechanisms are by drift and bounce resonance. I'm going to focus on drift resonance today, but we can talk about bounce resonance later if you like. So what happens? So particles have 3 fundamental ways of moving in a magnetic field. They have their very fast gyro motion. They're executing their Larmor orbits around field lines. They can bounce between mirror points along field lines, and they can also drift around the planet azimuthally. And so looking at the drift, there's a resonance. What do we mean by drift resonance? when the speed with which the particle is drifting around the planet, this matches the azimuthal wave phase speed. So you can think of it like the surfer on the beach, and so when the surf is catching the wave, there's a matching between the surface speed and the wave speed, and that's encapsulated by this criteria here, where the wave frequency is related to the m number, which is the azimuthal wave number, and the drift frequency. So basically, the particle is seeing a contribution to its velocity by the wave electric field. And we can look into this in kind of the simplest possible ways to look at some simplified equations of motion. So starting from and basically the point of this is to take you, I've been going back to school with this and reading these old papers and trying to teach myself it. And so I figured the way that I taught myself these things, I would try to share with you guys. So rather than coming at it from some expert opinion, I'm trying to take you through the journey I've been on over the last sort of year or two working through this. So we're looking at the guiding center equations. Guiding center just means that we're averaging over this much, much faster gyro motion, which is happening so much faster than ULF wave timescales, that we're going to average over that. We're also, for simplicity, going to assume that our particles are just sitting in the equatorial plane, or 90-degree pitch angle. It's an assumption that lots of previous studies have made, and it's also where I'm starting with for this. And you can write down these equations for the motion of the guiding center in cylindrical coordinates in the following way, and this is from Degeling in 2007. And so what you can see is that you've got the contributions to the change in time of the radial position and the azimuthal position are associated with the electric and magnetic fields. And so the first and second terms on the right-hand side here are the E cross B drift and the grad B drifts, respectively. We don't have any curvature drifts here because we're not assuming that we've got motion out of the equatorial plane at the minute. And so you can solve these equations quite simply. I used the Runge-Kutta scheme, and to see the effect of different fields in the particles, and lots of previous studies have done this. This m is the magnetic moment, which we assume is conserved, and it's an adiabatic invariant associated with the gyro motion. The gamma is the sort of relativistic factor, and q is the charge. So looking at what this gives us, as now the zoom bar is in my way. But anyway, so we've got, so this is just an example. On the right-hand side, this is just test examples that I've been doing to kind of try to teach myself this as to what's going on. The bottom left-hand side is an observation from Manital looking at drift resonance in spacecraft data. But picture the scene, focus on the right-hand panels for the minute, that you've got drift resonance for an m equals 2 waves. That means you've got 2 wavelengths going all the way around the planet. 20 keV electron at L equals 5. So what does this mean? So we've got a black line here, a black circle at L is equal to 5. The red dashed line is giving us a kind of cartoon depiction of the sign of the wave at that location. So here we'd have a negative electric field, positive electric field. So when the red line is beyond this circle, it's positive, and when it's inside, it's negative. So you can see that it goes negative, positive, negative, positive. So there's 2 wavelengths as you go around. And if you apply a propagating azimuthal electric field here, and you choose the wave frequency so that it's drift resonant with a 20 keV electron at L is equal to 5, what you can end up with is if the particle starts at a 0 of this wave, a node of this wave, all this particle is going to do is move around at exactly the same speed as the wave. And so that's basically what it's doing here. So the particle has moved from the left-hand one here to here. It's still sitting at a 0 amplitude of the wave, and therefore it's just staying on this one L shell. And so that's what you have here. The L shell is not changing. If, however, you started it at a different phase, so of the wave, so say you started it here, it would first of all see a negative electric field, and that negative electric field would move it radially inward. So if I go back to the equations briefly, if you had a negative azimuthal electric field, you could see this negative here would move this radially inward. So that's basically what that would be doing. And then what happens is as it moves to a different position, to conserve its magnetic moment, it's moved to a stronger region of field strength, therefore its energies had to go up, its kinetic energies had to go up, and it'll also have a different drift frequency. And so it kind of detunes itself from the wave. And so then it goes through this process of kind of drifting in the wave phase. And I do have a movie of this process that I'm hopefully going to exit out of. And hopefully you can let me know. I'll presume that if Rosie doesn't wave at me, you can see this. And so I'll just kind of skip through this. So unfortunately, this is not in red, but it's basically exactly the same plot as you've just been looking at. And a little dot is our particle. And so here it starts at some location. I'll just play it through first of all, and you can see what happens. So it moves inward. It's then in a region of positive field, and it's moving outward. And then as the wave goes around, it sort of detunes itself and then comes back in. And you can match all this up with exactly when it's seeing positive and negative fields and so on. And so this is the idea behind kind of basic drift resonance 101, which is what I was trying to get across to myself and hopefully have managed to get across to you guys in some way as well. This kind of picture on the bottom right-hand side is similar to what was seen in these observations by Magnetosphere. And so you can see there was the top panel here is showing this oscillation in the ground magnetic field data, and then these similar frequency oscillations in the fluxes of energetic particles which were observed in space. So it's a direct modulation of the particles by the kind of coherent ULF wave. You can then go and make these kind of cool things, which are called Planck array or phase plane plots. And so the top two are made by me. The bottom two are from papers by Degeling and Elkington. And so going back to that idea, if we think of this m equals 2, so there's two wavelengths in azimuth. We've got radial, so this is like L shell, radial distance on the y-axis. And then this is the kind of against the wave phase, so relative to your position in the wave. And so if you were if I go back a slide for a minute, if you're one of these positions where you're sitting at a 0 amplitude of the wave, then all you're doing is you're essentially sitting at this one location. So this would be one of these dots here, or this middle point here. If you start at a different phase, you can move out and in, and you do this in some kind of cyclic periodic way. And if you start particles at a whole bunch of different locations and also different L shells, you can kind of produce something like on the right-hand side. So if you've seen these plots in any papers, this is how they're produced. And you get these resonant islands forming where essentially the particles are trapped in between different peaks of the wave. Once you include, so this is for a kind of monochromatic ULF wave, and you see similar things here in the plots by Degeling and Elkington as well. Once you start to include multiple ULF waves, there's some sound going on right outside my office, I think. I do apologize. Once you start to include multiple ULF waves, you start ending up with the potential for diffusion. So that's where you get an overlapping of these different resonant criteria, and then the particles become diffusive or stochastic in nature. And that leads to a whole different field of radial diffusion and so on. And I know that there's a lot of people in the community interested in that. I'm not going any further than that today because this is about where I've got to in terms of my understanding of ULF waves and particles at the minute. So that's kind of where I'm going to be leaving that description. But the next step is going to be to look at using simulation wave fields to run test particles through and looking at the effect of 3D ULF waves on particles. Sorry, it's quite off-putting. I don't know what someone's doing outside my office, but they're doing something or other. And also what's the effect of azimuthal localization? So these kind of 3D ULF features that were confined to, say, in the plume structure, there's been some recent studies that have shown that they could be very important. The difference between field line resonances in fast waves, diffusion versus monochromatic excitation. So I feel there's a whole bunch of stuff that I can take from my ULF wave theory background and apply this in terms of particles. And I'd be very happy to talk more about this with people who are interested. I was going to talk about this, but I think I'm at time. So I have submitted a paper recently on looking at plasma pulse surface waves, but I spoke about this at the MIST meeting, and therefore I don't need to probably say it again to this audience because I'm sure you were all there and had a great time in Leicester. Conclusions, ULF waves are an important piece of the magnetospheric dynamics. I very much believe that we need theory and modeling to help us understand the observations. And we've got a lot of work to do regarding, I think, using realistic ULF wave spectra in terms of wave-particle interactions. And also there's loads of stuff I didn't mention. Didn't talk about high M, so these small azimuthal scale ULF waves. I didn't talk about PI2. This is kind of like night side substorm driven stuff. I didn't talk about measuring things on the ground and how they were affected by the ionosphere. I didn't talk about dayside transients. It's a whole bunch of ULF wave stuff that I didn't talk about here. But with that, I should stop there and just say thank you very much for your attention. So thank you.